Hi, I'm Lubo, and this is my Lab 3 video lab report. In this lab, I'll use fundamental physics principles such as the momentum principle and Newton's gravitational law to determine how the forces acting on orbiting objects affect their trajectories. A quick overview of my results. In part 1, I found the black hole in the system to have a mass of 1.3598 times 10 to the 34 kilograms, whereas in part 2, I found the necessary initial velocity of the spaceship to be negative 1.1 times 10 to the 7 meters per second in the horizontal and positive 9 times 10 to the 6 meters per second in the vertical direction. The purpose of this lab, in part 1, I'll use the star's observed motion around the black hole to find the mass of that black hole, while in part 2, I'll find the initial velocity the spaceship needs to have upon launch from the planet in order to get close to the black hole and then escape the black hole planet system without crashing. The fundamental physics principles I'll be working with in this lab are Newton's second law, the momentum principle, relating the change in momentum of an object to the force acting on it. I'll also use the momentum update formula to keep track of the changing momentum of the star, which will be used to update the velocity and position of the star. Newton's gravitational law will be used to derive the mass of the black hole from the force it exhibits on the star in part 1, while the change in momentum will be monitored by looking at both the parallel and perpendicular components of the star's momentum. To find the mass of the black hole in part 1, I'll use the known mass and velocity of the star at different data points in order to find the momentum change the star is experiencing, from which I'll find the net force exhibited from the black hole, and with the use of the gravitational law, the mass of the black hole. In part 2, I'll find the net forces acting on the planet and spaceship whilst they are in orbit around the black hole. From those known net forces, through trial and error, I'll determine the initial velocity the spaceship needs to have in order to get close to the black hole and leave the system without crashing. For part 1, the main assumption is that the gravitational force from the black hole is the only force acting on the star. The initial conditions for this part of the lab can be seen in this block of code on the left. For part 2, the main assumption remains pretty much the same. The only forces acting on the spaceship are the gravitational forces from the planet and from the black hole. Once again, the necessary initial conditions can be observed in the block of code on the left. In part 1, I used the already known velocity of the star at different time intervals to find the initial and final momentums of the planet. Those were used to find the change in momentum between different data points, and from that, the net force acting on the star from the black hole. The average of those net forces was used to find an average value for the mass of the black hole, which was 1.3598 times 10 to the 34 kilograms. Here you can watch a video of the star's motion around the black hole. In part 2, I used the already known mass of the black hole to find the net forces acting on the planet and on the ship, respectively. Code can be seen on the left. I then used those forces to update the velocities and positions of the planet and the spaceship. To find a suitable initial velocity for the spaceship, I played around with the starting velocity until I got a suitable trajectory that led the spaceship out of the black hole planet system. Here's a simulation of the planet and spaceship's motion around the black hole. Here, the cyan trajectory you see is the orbit of the planet, and the magenta trajectory you see is that of the spaceship. In part 1, a main source of measurement error leading to less precision with the calculation of the mass of the black hole was the fact that each time step lasted a whole day. In part 2, the time-consuming nature of the trial and error method stopped me from finding a trajectory for the spaceship that passed closer to the black hole. What does it mean question relates well to part 1 as it deals both with the net force and change in momentum. In this particular case, I was able to find the star's change in momentum directly using the known position, velocity, and mass of the star at different time intervals. Although equal to the change in momentum, the net force in this case is different as I couldn't calculate it directly from observation of the star's motion. While trying different initial velocities for the spaceship, I found that there are a lot which take the spaceship in a circular or elliptical orbit around the black hole. Here I have provided 2 example starting velocities for the spaceship, which take on a circular and elliptical orbit, and have shown how those orbits look here on the right.